Edexcel Corpio, complex numbers 6, the exponential form. Summing series using De Moivre's theorem. There is some important prior knowledge needed for this section of the course. We need to be familiar with a geometric progression, or you might call that a geometric sequence, which is a list of terms following a pattern. You also need to be familiar with the idea of a geometric series, which can be found using this formula, which is the total of the terms, and if the common ratio, the modulus of common ratio is less than 1, then you can find the sum to infinity using a over 1 minus r. And of course we're going to be using the binomial expansion when appropriate. So now if we look at summing series with complex numbers, so here we have a complex number geometric series here, and we're going to look at the sum of this series. So if we consider the example here, a is 1, so we'll look at 1 plus z plus n squared plus z cubed, etc. So a is 1. The common ratio is z itself, which can be written in exponent form as e to the I theta. Therefore the sum of n terms of this pattern is 1 minus the ratio to the power n over 1 minus the ratio, which using De Moivre's theorem can be written as 1 minus e to the I n theta over 1 minus e to the I theta. And we're going to be using some of these ideas of summation of geometric numbers in the following examples. So now we're going to look at an example which involves a binomial expansion, and I hope you recognise the right hand side of this as being the binomial expansion of 1 plus z to the n. We've equated this to something called c plus is. Notice the capital C and capital S. Capital C is used to represent the real part of the problem, in other words all the cosine elements, and capital S is used to represent the imaginary part, in other words all the sine elements of the pattern. Don't confuse capital C with the combination C used in the binomial theorem. So now we're going to write c plus is as 1 plus z to the n, where z is our complex number e to the I theta. So now if we first look at 1 plus z before we do the full solution, so dealing with the 1 plus z first, that's 1 plus e to the I theta. And a neat way of writing e to the I theta is to break it down into e to the I theta over 2 times e to the I theta over 2. But we can also do something similar with the 1. I'm going to write 1 as e to the I theta over 2 times e to the minus I theta over 2. So if we now pull out a common factor of e to the I theta over 2, I'm going to reverse the two terms just to make things a bit clearer in this bracket. And if we have a good careful look at that, we can see now that we can use our definition of cos theta over 2. So this can be now written as 2e to the I theta over 2 cos theta over 2. So now we know that 1 plus z can be written as 2 cos theta over 2 e to the I theta over 2, we can now consider c plus is, which is 1 plus z to the n. So now we can raise this to the power n as well. So if we now raise this bracket to the power n, and at the end apply De Moivre's theorem, we get e to the I n theta over 2. And if we now write this term back into its modulus argument form, we can now write this as 2 to the n cos to the n of theta over 2, and this can now be written as cos n theta over 2 plus I sine n theta over 2. And if we were, for example, looking for C, so if we wanted to pull out all the real parts of this original series, then we would look at the real part of this to find C, and C would be 2 to the n cos to the n of theta over 2, and the real part comes from this term here, the cos n theta over 2. So when using this binomial theorem, the important steps were rewriting the 1 using exponents and rewriting e to the I theta, which allowed 1 plus z to be written in this very helpful form. Then using this result, we were able to split e to the I in theta over 2 up into its real imaginary parts, from which we can find the real part of the series, which is capital C, or we could even find the imaginary part, which is capital S. So the first thing we've got to do is to find the answer to this little expression here. So expanding the bracket, we get 4 plus 2 e to the I theta plus e to the minus I theta plus 1, and then we can rewrite this bracket as 2 cos theta, and this becomes 5 plus 4 lots of cos theta. So now we're going to use this result to simplify this series here. Before we can simplify this series, we need to introduce our capital C, capital S notation. So I'm going to write C plus IS is 1 minus cos theta over 2 plus I sine theta all over 2 plus cos 2 theta over 4 plus I sine 2 theta over 4 minus dot 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 dot. And if we look carefully here, the imaginary parts of this, so if you're looking at the imaginary parts of this, form the negative of the summation that we're trying to find. So the summation that we're trying to find here is the negative of capital S. That's what we need to find, the negative of capital S. The reason I need to write it in this form is so I can write it as 1 minus a half e to the I theta plus a quarter e to the I 2 theta minus an eighth of e to the I 3 theta. So now we have a geometric series where the first term is 1 and the common ratio is minus a half e to the I theta, which means because the common ratio, the modulus of it, is less than 1, we can now think about finding the sum to infinity of the pattern. So before we move on, just to remind you that we are looking for the negative of capital S, that's the defined series. So now looking at C plus IS, we know it has a first term and a common ratio, therefore we can now find its sum to infinity, a over 1 minus r, which is 1 over 1 plus a half e to the I theta. And if we just tidy that up a little bit, we can write it as 2 over 2 plus e to the I theta. And then using the result that we found in the first part of this question, I'm going to times top and bottom by 2 plus e to the minus I theta. So the top can be written as a helpful 4 plus 2 e to the minus I theta, and the bottom becomes, using the result at the top, 5 plus 4 cos theta. Notice we have no complex numbers in the denominator now, having used the result at the beginning. And now rewriting the e to the minus I theta, we can write this as 4 plus 2 cos theta minus 2I sine theta all over 5 plus 4 cos theta. So now we can pick out S. So S is the imaginary part of this. So we're focusing on the imaginary part of this answer. So picking out S, we get minus 2 sine theta over 5 plus 4 cos theta. But we needed to find the negative of S. So minus S must be plus 2 sine theta over 5 plus 4 cos theta. That is the summation required. So the important steps there were defining this series as the negative of S and using that to create something called C plus IS. Once we'd identified C plus IS in exponent form, we could pick out the first term, the common ratio, and therefore we could apply a sum to infinity. Once we found C plus IS, we then picked out the imaginary part of the answer for S. So the imaginary part was S, and the summation that we found at the end was the negative of that. So just looking at some of the key points here, you can now use complex numbers to evaluate certain summations of real quantities. And you can use that more easily perhaps than other methods. De Moivre's theorem is a great way of simplifying problems, and it can be used to represent multiple angles. It's also well worth considering, is it worth rewriting an integer in this form? For example, we rewrote 1 as e to the I theta plus e to the minus I theta at one point, or we used that result. And the exponent definitions of cos theta and sine theta are also extremely useful. And that brings us to the end of complex number 6, exponential form.